All right, now let's use what we did in the previous video and practice. This is where we start to master these skills and really put it into practice. So we'll start with this first example. There are initially 72 houses. Initially 72 houses in a neighborhood. More people are moving to the neighborhood, and there is a steady rate of housing increase of 4% per year. In 5 years, how many houses are in the neighborhood? We've got all the information we need here. We know that we're dealing with exponential growth because it's a housing rate of increase, not decrease. So we can use our exponential growth formula, which we know is the total amount equals the principal amount times 1 plus the rate to the t over n. Start filling in the things we know. We want to know the total amount. We're starting, our principal amount is how many houses begin in the neighborhood. So at the beginning, we have 72 houses. Then it increases by 4% each year. So our rate is 4% or 0.04. And we're going to raise that to the t over n. Now, 5 years is our amount of time. It increases 4% every year. Since it doesn't increase 4% twice a year or 3 times a year, n is just 1. It's making that increase 1 time each year. So our t is going to be 5, our n is going to be 1. So really, we have 72 times 1.04 to the 5th power. And at this point, you can just throw that into the calculator to get your total amount. And when we do that, we get a total of 87.599 houses. And again, we're talking about houses, so you can't have, or you probably don't have, 0.59 of a house that's built. So when we're talking about how many houses are there, well, there are 87 full houses in that year. So we used our exponential growth formula, and we were able to figure out that in that year, after a 4% per year increase, there's going to be 87 houses after 5 years. Let's practice it again. A virus is now spreading through a network of computers such that each minute 25% more computers are infected. So we don't know how many computers we begin with at this point, but we do know that each minute it's 25% that are being infected. If the virus began with just one computer, construct a formula to model the exponential growth. So we're dealing with exponential growth, that's good. We know that that's going to be the total amount of computers is going to equal the principal amount, which in this case is 1, times 1 plus our rate, which is 25%, all to the, now our time, in this case, is each minute. We don't know yet how many minutes we're going to calculate. It says we just need a formula to model for each minute. So each minute, the 25% increase kicks in. We're going to use each minute as our time, which means that our n is just 1. So really, we don't even need to put that over 1 because it's not going to affect anything. So we can just say plus 0.25 to the t power. All right, so how many computers will be infected in 5 minutes? Well, let's plug it in. Our total amount of computers will be 1 times 1.25 to the 5th power. And when we throw that into a calculator, we get 3.052. But we know that we can't have 0.052 computers, so our answer is 3 computers. Starting to make a little bit of sense, I hope. There's 2 examples. Let's do our third. In this case, we're dealing with the value of a pair of Air Jordans from 1993. It appreciates in value, and that's an important word right there. Appreciates in value. What does appreciates mean? Well, that means that it increases. Each year, the value is going up by 6% per year. As you guys know, sneakers get more valuable over time, especially old Air Jordans. By 6%, we're going to construct a formula or a function that maps the exponential growth of the value of these shoes per year. Now notice it doesn't say how much the shoes cost at the beginning. It just says that in 1993, they have some value, and it's going up by 6% each year. So let's make sure that we write down all the things we know. We know that the total value is going to be equal to whatever the principal amount was, plus 1 plus 0.06 to the t over n power. Now again, we're going to use time as years. It's only appreciating once per year, so we can kind of condense this to be 1.06 to the t power. Again, n is used if this appreciation is happening more than once per our unit of time. And we're talking per year. It's happening once per year, so t is just that time. So there's our formula. Now in 2016, how much are these shoes worth? Well, we still don't know the initial amount, but we can compare it to what the initial amount was. Whatever this principal amount was, times 1.06 to the, and in 2016, that's going to be 23 years later. So in 2016, the amount will be whatever the initial amount is times 1.06 to the 23rd. And if we raise 1.06 to the 23rd power, we get 3.8197, and if we round to the thousandths place, that 1 is going to become a 2. So our total amount is whatever the principal amount was, whatever those shoes cost initially, times 3.820. So we can't say what the exact cost is, but we can say that the shoes are worth $3.820 times their initial value. So if you looked up sneakers from 1993, maybe those things cost $60 back then. You would just plug that in, and you would have 60 times 3.820. And using that formula, maybe now they'd cost $229.20. So you could just use that to determine it. But they didn't give us the initial price, so we're just working with what we have. All right, so that's exponential growth. Now, using these notes, you'll be able to complete all of the questions on exponential growth in the back of your holiday packet. The next 2 videos will deal with exponential decay.